Okay, so we got example two, and example two is looking at a different scenario. Okay, in example two, we actually do not have these chemicals initially. So in this scenario, we do not have reactants, we only have products. Okay, so think about this logically. If I don't have reactants, can I use them up? No. If I don't have reactants, can I produce them? Yes. How am I going to produce them? I'm going to produce them from HI, which currently has some stuff. Okay. So what does that mean? Well, if I don't have any reactants, I have to produce them. So they are both going to get a plus sign. How much am I going to produce? They both have a coefficient of 1. So we're just going to give them X. HI, hydrogen iodide, is going to go down if these are going up. So I put the minus sign, and it's going to lose 2x. Okay? And again, you guys are going to feel comfortable using ice tables as we go through this unit. Now, the question becomes, how am I going to figure out what x is? Remember, you want to use a column that is entirely filled. So I can't use H2, I can't use HI, I have to use this. Well, thankfully, this is a very easy calculation. If I initially started with 0 and I add x, and that is equal to 0.242 moles per liter, then your 5-year-old sister should be able to realize that the 0 doesn't matter and x is 0.242 moles per liter. Okay, what does that mean? Well, 0 plus 0.242 is going to give me 0.242 for hydrogen. Sorry, I should write that in green because it's my green chemical. 0.242. Okay. And again, you can write that calculation out if you want, but I'm just doing it in my head. And then over here, we've got 2.20. Let's write this one out. 2.20 moles per liter minus 2 times 0.242 moles per liter is going to give us our equilibrium concentration. And it is 1.516 moles per liter. Okay, that's my blue concentration. So we've established the equilibrium concentration for each of the chemicals. Now all I want to do is plot them on the graph. So let's start with hydrogen. Hydrogen started at 0, so at 0 I'm just going to draw that straight line, and it went up to 0.242. Let's use the same scale. 0.5, 1, 1.5, 2. So it went up to 0.242, which is right around here, let's say. Again, doesn't have to be exact. I just want to see your understanding. It's not a straight line. It's not linear increase. It's a little more exponential. So I draw a little bubble. Now, the same thing happens for iodine. It's my red color. So I'm just going to draw it right above, although it is the lines are on top of each other. It's going to go up. So I draw my bubble, and then it stabilizes at 0.242. So that's iodine. And that is also the case for hydrogen. Okay. Last but not least, what we have to do is look at hydrogen iodide. Hydrogen iodide, it's going to have to be a little bit above 2.2. I'll just extend my graph, or above 2, sorry. It started at 2.2. We'll say that's right around here. Okay. And it went down to 1.516, which is right around there. And I'm just going to draw a going down arrow, or going down slope. Again, I don't want to see this. That doesn't really make sense right now. If it's going down, you should be slowly decreasing the concentration. Okay. And this is for HI. You can write these HI, I2, H2 over here. I don't care. But again, all I want you to be able to see is how the ice table allows us to find our equilibrium concentrations and how the graph shows us visually what is happening in this scenario.